But everything that we've talked about so far is just building up to bonding, which is our next unit. So understand that, like, even if you don't feel like 100% confident on what you're doing so far, like, you're gonna keep getting more practice, but it isn't something that's going away either. So you need to kind of make sure, like, you keep practicing it. The more comfortable you are, the easier next unit's gonna be for you. So I just kind of want to put that out there. It's not like this is a one and done and, you know, we're gonna move on and never see this stuff again. All right, so we're going to keep after it here for a couple units with our chemistry. It's all kind of similar. So we said, just like the video showed, our goal is to be stable if you're an atom, right? But we know that neutral is not always stable. So it might be neutral where you have those equal number of protons and electrons, but it doesn't mean that it's stable and that that's where it wants to stay and that's where it's happy and it's satisfied. All right, so what makes it satisfied is if you have that full valence, and that's in group 18 or valence group 8. Okay, so again, this is slide number 64. There's a few slides we skipped. That's okay. Maddie's like, what? Okay, yeah, so it's okay. We skipped like 3 or 4 slides. That's something that's not necessarily covered. So I added in case we're like ahead of schedule, but we're right on track, so we're going to keep on moving ahead. And again, the reason that they're satisfied and stable is because they have that magic number. What is that magic number? How many electrons are they trying to get in their valence? 8. What's the special one that only has 2? Helium, right? Because it's so small, it only has that one energy level. Good. So elements that don't have a full outer valence are going to form something called ions. Again, ions is a weird word. I get that, right? All it's talking about is that it is an atom that has either taken on electrons or given up some electrons. If they take electrons, now they have more negatives, they're a negative ion. If they've gotten rid of some electrons, then that means that they have more protons. Protons are positive, so they're going to be positively charged. That's all it means. You've either given some electrons or taken some. And ionic charges are able to be predicted by their group number. That's why the valence groups are so important. That little group at the top of your periodic table that's in my handwriting that are circled, right, and that you color coded, like mine I think were green, yes. You might have picked a different color, but those valence groups, where we ignore those short stacks, those little short columns of metals, because they're not predictable, right? We only are going to look at the valence electrons, okay? So elements in group 1 have 1 outer electron. We know that. That's what put them in that group with all the others that have 1. All they need to do is get rid of that one. If they can get rid of it, kick it out of there, then they drop down to that next energy level. And remember, you don't move up an energy level until the one below it was full. So since it's full, now they're stable and satisfied, even though they're charged. So sometimes in our mind, we think, oh, if it's neutral, then it's good. Neutral isn't always good, right? Sometimes it's better for these to be charged. And what we mean by charged is not like fully powered, like a cell phone or your laptop or something. We mean an unequal number of protons and electrons. All right, and so there's the big kicker. Neutral doesn't always mean stable. And that's why we get those ions forming. They're going to do whatever they can to get stable, which means giving up being neutral, but it's fine. That's the way they want to be. And this is the reason why, even though we only have 118 elements, we have a lot more than 118 things in our world, right? We have a ton, like in this room alone, you know, who knows how many different hundreds or thousands of different combinations of compounds we have. The reason they want to form these compounds is because they form ions, and just like the video showed, the ions are kind of, you have an opposite attraction, right? You have a positive charged atom and a negatively charged, they come together, okay? And it's because of that that we get all these different compounds naturally forming. So this slide is super important because it shows us the ions that it's going to form. All right, notice our little short stacks, our short columns here, are groups that do not go all the way up to the top. They say variable charges, meaning they can form a +1, a +2, a +3, right? We don't know, we'd have to be given more information. Variable meaning changing charge. So sometimes they can form a 2, sometimes they'll form a +3, sometimes a +1, right? These ones though are always going to be a +1, a +2, or a +3. Now, when you see the plus sign, that doesn't mean you're adding negatives. What that means is the charge that the atom now has, and that confuses people because you see that plus sign and you think, oh, okay, I'm adding electrons. Well, if you're adding negatives, it would really be making this negative. These ions are positively charged because they have either given 1, 2, or 3 electrons over to a nonmetal, and they've gotten rid of some. So if you have less negatives, now you have something that's positively formed, or positively charged. And so this is another one of those things that I'm gonna beg you, do not try to memorize this. First of all, just use your periodic table because it'll show it on there. Second of all, think logically. You get rid of negatives, well now you have more positives. You're positively charged. If we go over here to the other side, remember I said valence group 4 is kind of that funny one, where 4 is right in the middle of 8. So they can either get rid of 4 and form a positive ion, or they can take on 4 and they become a negative ion. So they're right in the middle. So this group, it's going to do something with 4. Either get rid of the 4 or take the 4. But I would have to give you more information on that. Like you wouldn't know just by looking at it what it's going to do. I'd have to tell you, or it'd have to be on, the paper somewhere. But if we go to valence group 5, valence group 6, and valence group 7, we know exactly what they're going to do. They're going to take 3 for group 5, 2 for group 7, and 1 for group, did I say that wrong? 3 for group 5, group 6, and 1 for group 7. Okay? Because we're still trying to get up to 8. So 5 plus 3 is 8, 6 plus 2 is 8, 7 plus 1 is 8, right? Now, this is a negative charge, not a minus sign. So just like this is not a plus sign, this is showing a positive charge. This is not a minus sign, so we're not doing addition and subtraction. You're not subtracting 3 electrons. They're actually taking 3 electrons. So in our mind, we a lot of times want to think, okay, well that positive means I've had to add something, that negative means I had to lose something. These are not adding and subtracting. These are dealing just with charge. So it's telling me I have a positive 3 charge and I have a negative 3 charge. So if I have a negative 3 charge, that's because I've gained 3 negative charges, right? I've gained 3 electrons somewhere. Here they have gained 2 electrons, and here they've gained 1 electron. Okay, so don't think of the plus and minus as adding and subtracting. All right, ask yourself, what does the element have more of? Well, these all have more protons because you've lost some negatives, so that means it's positive. These all now have more electrons because you've added electrons, which are negative, so now you have more negatives. That's the charge. Okay. All right, so here's just another chart to show this. Valence group 1, 2, 3, 5, 6, 7. They say the 2-8 because of the helium there, but we know this is valence group 8. And again, they already have 8, so they're not going to form ions at all. They're that special group. Here, these are going to be our negative ions because they are gaining negatives. Gaining negatives means they're going to end up with that negative charge. These we can't predict, so we're going to kind of ignore. But valence group 1, 2, and 3, again, these are going to these are going to lose 3. So now you have more positives, making them positive ions. Another way to remember this, our metals are going to be positive. They are always going to give. Our non-metals, 5, 6, and 7 valence groups, they're going to be the takers. They are always taking those electrons. So these are always going to be positive. These 3 groups are always going to be negative. Like, no exception to that. which is nice. It's nice when it's like, bam, that's the way it is. Yes,
I figured out something.
tell me.
You can take oxygen and nitrogen, or no, not nitrogen, hydrogen and whatever makes water. And then you can take those two atoms and combine them together like two oxygen atoms and one hydrogen atom, and you can basically create water from nothing. Meaning you can create a machine that can synthesize water from nothing.
As long as you have the base parts to start with, yeah. Yep, that's how it works. Okay, so some of us are kind of visual and a little bit more hands-on. This little way to do this hopefully will help kind of make all this make sense, all right? I think you guys are doing a good job with what we've already covered so far. Adding in this last bit with the ions, sometimes you're like, huh, I just finally got the hang of what we were doing the first time. Now we're adding this other piece. This will hopefully help kind of visually make it clear. All right, so we're going to use this thing called Lewis dot structures or Lewis dot model. It has multiple names. It's all talking about the same thing, where basically we are going to look at valence groups and we're going to count up like how many more electrons that atom needs or it can lose, and it just kind of helps us see what's going on. All right, so we're going to find out which valence group or column our element's in. Notice we're just looking at these colored ones. Again, ignoring the transition metals and then the lanthanides and actinides, which are the synthetically created elements. Synthetically meaning like they can make them in a lab, they're not naturally found. Okay, so once we find the valence group, 1, 2, 3, 4, 5, 6, 7, or 8, we know that's how many electrons are in that outer ring. You guys all feel comfortable with that part by now, right? Okay. And so we're going to only count or use those valence electrons. We're not looking at total electrons, just the valence. So what you do is you write the symbol, which is like the abbreviation, right? So find carbon on your periodic table. So go ahead and get yours out if you don't have it out. I didn't already tell you to have it out. Find carbon. And you're looking for the valence group that carbon is in. So you should see it there in the 4th group. Okay. And obviously, on your paper, I don't know if you're actually starting at the right, but technically you're supposed to start by putting a dot here, then the top, then the left, then the bottom. All right, so starting at the right, you're going to put 4 electrons or dots, and we're going to go counterclockwise around the element. All right, so if you look up here, it's going to do it for me. So I go right, top, left, bottom. So around your carbon, your C, put those 4 dots. Each side can hold 2. So a total of, my dots out here. All right, so technically, if we wanted this to be full, we could add 4 more dots, right? Another one here, 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 and here. Now you have 2, 2, 2, and 2. That makes it full. What's the other option to make this satisfied and full?
To take away from?
Yeah, we could get rid of all 4 of them, and then it drops down to the next valence level, which was already full. So remember, since this is valence group 4, it has that option. You're going to do 4 of something. Either get rid of 4 or take 4. All right? So having it like this lets you visually see, oh, I'm 4 away from having a full valence. All right, so this either needs to be totally empty or have a total of 8 dots. That's what this is all supposed to help kind of show. Uh-oh, there we go. I lost my mouse. Okay, so if you check your work, you should see 4 valence electrons And you should have that match with carbon being in the 4th valence group. It is. So we have those 4 dots around the carbon, so we know that we did it correctly. All right. Just in case I forget to tell you too, I posted 2 more Kahoots in our unit links under the classwork tab. One's for ions and one is predicting ionic charges. So I added those on Friday, so you'll see those in there. So if you think you're like, whoa, I need some practice, do that Kahoot link on your own, okay? So you have like a little chart on your notes. We're gonna start with hydrogen. So I think it's already written for you, right, the H. And so we're just gonna start going around and adding in those dots. Oh geez, sorry. So find hydrogen on your periodic table. What valence group is hydrogen in? What valence group do you see? Breeze, where is it? Group 1. How many electrons does it have in its valence then? Good job, Charles. 1. And then how many dots is it going to need? Just the 1, right? So again, we started the right. Now, it's not, like, I don't think it's necessarily wrong, but I didn't make these rules. Again, they want you to go to the right, top, left, bottom, like follow that order. I don't know. So they don't want you to put the 1 just right up there, I guess. Okay. Find phosphorus. Atomic symbol P. Find phosphorus. What valence group is phosphorus in? Where do you see it, Charlie?
5.
Valence group 5. So how many electrons will it have in its outer energy level or in that valence? Cheyenne, do you know? What's that?
What'd you ask?
How many, if it's in valence group 5, how many electrons are going to be in that valence group? 5. So how many dots is it going to have for this dot model? 5. Okay, so right, top, left, bottom, and then another one to the right. Okay, so you should have that. You're bubbling those in. And remember, those dots are just representing those electrons. That's all it is. Okay. Any questions? Doing okay? Let's go to calcium. What valence group do you find calcium in? You find it.
2.
Everybody see it there in 2? So Brooklyn, how many electrons are in the valence for calcium? It's in valence group 2. Okay, how many dots are there going to be then, Owen? If it's in valence group 2 with 2 electrons, how many dots do we use?
Dots.
How many dots? How many electrons? We said the dots are representing electrons, and we said it has 2 electrons. 2 dots, right? If you guys haven't picked up, I'm just kind of randomly calling on people that I haven't heard a lot from. 2 dots, 2 electrons. So guess what? It wants to get rid of those 2, right? Isn't it easy to see that if it can fit 8, it's a lot easier to get rid of the 2 than it is to have to add all 6 of those, right? So for this to form an ion, it's going to get rid of those 2. All right, let's go back for a second to phosphorus. When it has 5, is it easier to get rid of those 5 or just add those 3? Add the 3. So this is going to form a -3 ion because now it has 3 extra negatives. Okay, it's gained 3 negatives, so this is gonna form a -3. With our calcium, if we had 2 and we get rid of the 2, now we've gotten rid of 2 negatives, leaving us with a +2 charge. All right, because those 2 are now gone, if I get rid of those, oh wait, I might have an X. Yes. If I get rid of these 2, right, no longer there. Ooh. Now I have more positives because I've lost some negatives. This is going to have a +2 charge. Kind of seeing how that works? Maybe? Slowly? Okay, argon. I always feel like a pirate when I say argon. What valence group is argon? Emily, where do you see it? Okay. Stewie, you find it?
Gases.
It's a noble gas. Fantastic. So how many valence electrons do all the noble gases have? Close. They just sit there on their donkeys. Good. They're valence group 8. So how many electrons is argon going to have around its little symbol there? 8. All right. So right, top, left, bottom, right, top, left, bottom. These are our electrons. There's 8 of them. 8 is that perfect octet. That's exactly where it wants to be. Everything is happy and satisfied and stable. It's not neutral. Maybe it is, maybe it isn't. We won't talk about that for these. Sorry. Don't want to confuse you. So if we have our 8, we're perfect. It's like that. Oh, nirvana, excellent state of happiness. Okay? Yes?
What would happen if you combined every element in the periodic table together?
Well, it won't work that way because not everything is going to want to combine.
It would probably cause an anomaly, making the whole entire universe explode.
I can't say that that wouldn't happen. I don't know. We don't know. Creative thought, though. All right, so these aren't going to do anything. They're not going to get rid of all 8 of these, and they're not going to take any more because they're already full. So this is as full as it gets, right? So this is perfection. All right, let's look at chlorine. Find chlorine on your table. Abigail, can you find chlorine?
It's in valence group 7.
Very nice. If it's in valence group 7, Anthony, how many electrons will it have in that outer shell? Chlorine?
7.
Good. So it's in valence group 7, has 7 electrons. So that means we're going to have how many dots? Okay. So right, top, left, bottom, right, top, left. Oh, we just need 1 more, right? We are 1 away. So is it going to be easier to try to get rid of? I don't even have enough X's. Are we going to try to get rid of all these?
Yeah.
Or just get the 1?
Get the one.
Let's just get the 1. Don't be difficult, boys. Right? Get the 1. So if I now have 1 extra electron, what charge do electrons have again?
Negative.
Negative. Now this is going to be negatively charged by 1. So a -1 is the charge. Okay? Let's look at aluminum, or if we're British, aluminium. Aluminum. Where are we going to find that? Is that your hand? Okay, what valence group? Valence group 3. So, if I'm looking at valence group 3, how many valence electrons do valence group 3 all have? Let's see, Austin.
3.
Okay, how many dots? Rory.
3.
Okay. Right, top, left. Now I stop there. So, is it going to be easier for this aluminum to get rid of 3 or to gain 5? Who thinks it's gonna be easier to get rid of 3? Good, right? Most of you. So, X that one out, X that one out, boom. If I get rid of all those, it drops down to the next energy level, which was already full, right? It's a lot more work to add, right? So if I get rid of the 3, now I have more protons, right? Because I've gotten rid of 3 negatives. What do I have more of? Protons. What charge do protons have, Stewie? What charge does a proton have? Good. So now I have a positive charge. A positive 1, positive 2, positive 3. Because I lost 3 electrons. Yikes. It's a lot for a Monday morning, huh? All right. So, let's take a look. I think, not tomorrow, soon, we are going to have an activity where you're gonna need to do, actually, hold on. Let's just watch the video first, and we'll do this tomorrow, I think. Yeah, let's do that. So let's just take a look at this video. That'll end us up because we won't be able to finish.